All right, so this is our last video in the intro part of the unit, or the first part of the unit, about impulse and momentum. It's about graphs. And so one fact that was relatively untouched in our energy unit is that the amount of work done is equal to the area under a force versus displacement graph. There's an analogous idea in the world of momentum. The impulse is equal to the area under a force versus time graph. So there's a lot of like redundant things in there, right? Like work is equal to the area under a force versus displacement graph. That also means that the change in energy is equal to the area under a force versus displacement graph. For impulse, impulse is equal to the area under a force versus time graph. That also means that the change in momentum is equal to the area under the force versus time graph. So impulse and momentum get exchanged, or change in momentum get exchanged all the time. And so I'm going to kind of show you that in an example. But the first part of this lesson is I just want to show you what a typical graph would look like. And so, if we did the tennis ball getting hit by the racket example in the previous video, anything that's like that sort of collision, it works. It can be like a car accident also, but it could be just like a ball hitting the ground, which is our example problem today, or anything. Any sort of collision usually doesn't last a ton of time. And so the graphs tend to look like this. They tend to look like a bell curve, basically. They're not always symmetrical. They're not always asymmetrical, because I do that. They're usually pretty symmetrical. In the real world, they're not, but in our universe, they're going to be very symmetrical. So the idea is the collision starts at a certain amount of time, and the force really quickly ramps up and really quickly ramps back down to zero. So, the force is equal to zero before and after the objects collide, and then the force changes, you know, to some magnitude while that happens. This shape of graph is due to the compression of objects when they're colliding. And so if you think about like a tennis ball is hollow on the inside and it's made of like cardboard and felt and compressed air. When the ball hits something like a racket, it's going to compress and then it's going to release before it leaves. That compression, when the compression starts, the force increases until the objects are at maximum compression and then they release. It's essentially elastic potential energy getting stored and then released. And one of the consequences is that you get a graph of that shape. Now, in our world, we don't deal with curvy graphs and areas under the curve because that's the job of calculus. So this being an algebra-based class, we don't do that. What we do is we understand that a couple of things, that when we look at graphs, they're going to have like geometric shapes. So they're going to have straight lines. And also we're going to understand that there is some average force. So we can take a curved graph and say that there's also overall this changing force over a certain amount of time is the equivalent of a constant force over time. Whatever that constant force is the numerical average of the graph. So, that's it for really the intro. If I wanted to find the impulse, I would find the area under the graph, and that would equal the impulse. That would also equal the change in momentum. What follows is a fairly lengthy problem that involves a force versus time graph, and so I would encourage you to watch it. It is very complex relative to a lot of the problems that we've done so far this year. It relies on multiple units. It's a pretty good problem that relates to multiple topics. And so I think it's like a good problem, but it is pretty complex. The actual like lesson is very short. So here we go. This is going to take a while, so feel free to like skip around if you want. So we have a ball that's dropped from a height of 1.5 meters. The floor exerts an upward impulse that produces the following force versus time graph. How high does the ball bounce? So you've learned a few key units in physics so far: forces, circular motion, energy, and now impulse. And so, one of your goals is going to be to learn how to choose the topic. So if you don't know how to choose, then maybe you like draw it and see what happens from there. So I'm going to draw this story in three parts. In the first part of the story, the ball is dropped from a certain height. It falls. In the second part of the story, it's squished here on the ground. And in the third part of the story, it moves up and stops at some other height. Now, for those of you who did the ball drop lab, this might sound familiar, that you drop it from some height, it bounces off the ground, and it ends up at some other height. Whether we've talked about it or not, there is an energy loss due to the ground when that collision happens. And so the amount of energy that the ball has at the beginning is greater than the amount of energy the ball has after the bounce, the first bounce. So basically, I'm going to solve this problem in three parts. The first and third parts are free fall motion. So, if I reduce this to part one, part two, and part three, I can kind of summarize. I can say 1 and 3 are maybe kinematics because they're just falling through the air, or energy because that looks to me like a conservation of energy situation. But part two, when it's actually on the ground, that is an impulse concept. So I can solve this problem in any way that I want. Now I have the advantage in that I know how to solve the problem already, but you might not. So I'm gonna just do some random things and try and my best as I can talk you through what you would think about. So you're given this word impulse and you have a graph. And so one thing you know is that the impulse is equal to the area under a graph. So we're gonna actually look at that interaction. So impulse equals area. And that area is equal to, it's a triangle, so 1/2 base times height. So I can do J equals 1/2. The base, it goes from 0.006 seconds to 0.018 seconds, so that's 0.012 seconds. And then the height, the peak of the triangle, is at a force of 400 newtons. Okay, and so the impulse, 0.5 times 0.012 times 400 is 2.4 Newton seconds. Now, there is a bit of significance there. 2.4 newtons per second is a positive number, right? This graph is above the x-axis, so it's a positive area, it's a positive impulse. This is the amount of momentum that the ball gains when it hits the ground. So the ground exerts an upward impulse. To kind of follow along with this, let's look at basically the only equation that we know from this unit so far. And hopefully we can start to see things come together. So the 2.4 is the impulse. That's the left-hand side of the equation. It's also the right-hand side, but whatever. 2.4 Newton seconds is the impulse. The other thing I want to keep in mind is the ball has a final and initial velocity that's associated with specific locations in my picture. The initial velocity is going to be right there. Because the impulse equation deals with the interaction between the ball and the ground, the initial and final velocities happen exactly on either side of this. So the initial velocity of the ball is not 0. It's actually whatever this number is as the ball hits the ground. That's V0 here. The impulse takes hold, and that causes the velocity of the ball to change to whatever this number is. So the V in this equation is right after the bounce. The V0 is right before the bounce. And so I have a little bit of work to do to figure out that. So I'm going to do number 1 next, and my goal is to find V0. Now, this is where things get tricky because you have a 3-part problem. The end of one problem is the beginning of the next problem. So I'm going to have to keep that in mind. Now the ball is released and it falls 1.5 meters. So I can use like whatever equations I want, but since we just finished energy, why not just use energy? This is a transformation between gravitational potential energy and kinetic energy. So the ball starts with a certain amount of energy. It ends with the same amount of energy. And this V, I'm actually going to put V naught in there. I know that it's final energy, but I want it to match up with this. The V naught is that value right there. So the gravitational potential energy is here. It falls, gains kinetic energy, and so that's what this equation is going to tell us. Now, I can cancel mass. V naught is equal to the square root of 2g delta y. If you used kinematics, you would have gotten the same expression out of this. So 2 times 9.81 times 1.5, square root of that. And I have 5.4. Okay, 5.42. Okay, here's where I have to be very careful, because when you use an energy equation, and if you use that kinematics equation, you don't generally get the right sign out of things. You have to think of that yourself. So the speed of the ball when it hits the ground is 5.42 meters per second. That number has to be negative because the ball is traveling downward. The kinematics equation and the energy equation that would go along with this would not tell you that. So you're going to have to infer a lot about things in this unit because not every physics equation is equipped to tell you the right direction of a vector. So negative 5.42 is the speed of the ball right before it hits. The next thing I'm going to do is I'm going to find V. Now, this is going to look even different from what we just did. I can't use kinematics or energy here because I don't know what height this is. That's the eventual question that I'm being asked. So I'm going to find V using this equation. So force times time equals mv minus mv naught. And I'm like ready to plug this in already. The impulse was 2.4 Newton seconds. I can combine mass. I think that's going to be fine. So 0.25 kilograms times V minus negative 5.42. So I have to solve that. So notice what's happening. I'm ending up doing this problem in sequence right now. I found the velocity with which it hit the ground. I also found the impulse from the ground. And I'm now using the initial velocity and the impulse to find the final velocity. So I can kind of talk you through my algebra. I would do 2.4 divided by 0.25. I would take that answer and subtract 5.42, and I would get 4.18 meters per second. Now, when an object bounces off the ground, it's traveling downward and it hits the ground. When it bounces, it travels back up in the air. So this number should be positive, and it is. So the impulse momentum equation is equipped to tell you what direction things are traveling in. It's really just this conservation of energy idea and the kinematics equation that would result in this that don't tell you what direction things are moving in. So we now know that the speed of the ball is 4.18 meters per second after the bounce. Now I need to find the height that the ball reaches. And so I go either back to energy or back to kinematics. So just to show you a variety, let's do kinematics. The issue with this is, again, like this V, the 4.18 meters per second, is final velocity, but it's really the initial velocity of this event. So once the impulse ends, the kinematics takes over. In this world of kinematics, this height is associated with a velocity of 0. So that's the maximum height that it reaches. So I have 0 squared equals 4.18 squared plus 2 times negative 9.81. X minus x naught. X is the value that I want. X naught is 0 because it was on the ground. So x, it really should say y, I guess, but it doesn't. So I'm solving this. So I would do 4.18 squared, and I would move it to the other side. So I'd have negative 17.4724. I would divide it by 2 times negative 9.81, and I would get an x of 0.89 meters. And wow, that's the answer to the problem. So I hope that this has been a useful journey in some way. Just to, if you're done with the video, that's fine. But if you want a summary, here goes. The object fell to the ground. When it's falling, gravity is the only force acting on it, so I can either use kinematics or conservation of energy. So that's kind of an important thing to understand, that when a conservative force like gravity is acting and is the only force acting, you get a choice, kinematics or energy, and both should work. In the middle of this problem, it hits the ground. And so collisions are the world of impulse and momentum. So any collision, you want to really focus your understanding on impulse and momentum. And to give you like a preview, impulse, if you have information only about one object, momentum, if you have or want information about both objects involved in the collision. And then once it bounced, kinematics and energy took over again because gravity was again the only thing acting on it. So we will probably do a problem like this in class, and we will do a lot more kind of simpler problems with impulse and momentum. Thanks.